probably to the 10th of November 6th. So let's pick up this tradition and continue. We're going to hear about the TA experiment. Go for it.
Thank you very much. Thank you very much for inviting. I'm happy to talk here. And I talk about overview of the recent results and the future development of telescope array experiment. And first, I talk about the latest results of the TA experiment. And here, I focus on the implications of anisotropy results. That will be related to unknown origins of ultra-high energy cosmic rays. So I focus on that. And then I talk about the TA times 4 experiment. This is an extension of TA experiment. All right. This is members and 35 institutes, 7 countries join this collaboration. And this is a map of detectors. And the red point is corresponds to the location of the SD, and the SDs are surrounded by 3 FD stations. And the SD has 1.2 kilometer spacing and covering about 700 square kilometers. And there are totally 507 SDs. And SD consists of 2 layers of 3 square meter area, 1.2 centimeter 6 plus 6 centimeters. This coverage is, thanks to this coverage, is the largest cosmic ray observatory in the northern hemisphere. And hybrid observation by this SD and FD started from May 2008. This site is located in Utah, in the USA. And for the extension to the lower energies, we installed other FD station here. This is known as TeVPA experiment. This is a field of view of extended the new FD station. And TeVPA FD was installed in 2012, and operation started since 2013. And in addition to that, the dense array, SD array, was installed here, the totally 80 SDs. And the hybrid is implemented 2018. And this is the introduction of detectors. And this is analysis procedure, event reconstruction with SDs. This is a footprint of the SD of cosmic ray event. And the size of the circle corresponds to the number of particles. And the color denotes the timing. And from timing information, we reconstruct the shower geometry. This is a figure of fitting of the timing. And this is a fitting of signal density of detectors. This is known as lateral distribution fit. And using this fit, we estimate signal density at 800 meters from shower axis. And then using that parameter, we reconstruct the primary energy. And this is event reconstruction with FDs. And this is the event display. And we compare the longitudinal development with Monte Carlo, and we measure the X-max. And we integrate signals of PMT. Then we calorimetrically we can measure the primary energy with FDs. And we use actually the FD energy for also for the SD for accuracy. And we make a relation between SD and FD with hybrid events hybrid SD and FD hybrid events, and we make a relation between the SD energy and the FD energy, and we rescale SD energy to the FD energy, and we show the analysis results from the next slide. Okay. So from this slide, I shows a result of analysis using these detectors and using these analysis procedures. And this is energy spectrum obtained by 11 years observation of TASDs. And the black point corresponds to the data points. And we can see clear break at the ankle and a cutoff. And recently, Auger found a new break at 1.3.10 to the 19 electron volt here. Then we also combine with other data to find, to estimate that feature is correct or not. And this is TSD and TFD. And this is also a high-res result as an experiment. And we combined all of these data. We also found a break at 10 to the 19.25 electron volt. And significance of the break was estimated to be 5.3 sigma using this combination of the data. And the combination of TASD with tail FT mono results, we obtained this wide energy spectrum at this wide energy range. The energy range corresponds to about 5 orders of magnitude. And we can see some clear breaks from the energy spectrum, knee here, and break, and second knee. And as I showed in the previous slide, is the ankle. And combined with other data, maybe we also found another break here and a cutoff in this energy. And we compared this result with other experiment. This is a comparison with Auger results, and energy is rescaled by 10% because there's a systematic of energy, and this rescaling 10% is within the systematic uncertainty. And also this is, it looks like also the discrepancy at low energy, but this was updated by the latest result. So the discrepancy at low energy looks smaller using the latest results by Auger results. So we focus on the discrepancy at the highest energies. So this is, we can see is a clear difference at the highest energy between these energy spectra. So triggered by this discrepancy, we started to discuss in the Auger and TA working group of energy spectrum. And also in the TASD, we also separated our energy spectrum into 2 regions. One is energy spectrum in the common declination band with Auger, and another, and they also split it into 2 regions. One is a common region and one is outside of the common region. And we found some difference of feature of the energy spectrum. The implication of the lower declination band, the cutoff energy is estimated to be like this, and and higher declination band is estimated to be like this, and the significance of the cutoff difference of the cutoff energy is now estimated to be 4.3 sigma. So then I move on to the anisotropy result. We keep updating the anisotropy result of the known as TA hotspot above 57 eV. eV means 10 to the 18 electron volt. This is significance map from isotropy expectation reported in 2014 using 5 years of TASD data. This map is drawn with 20 degrees oversampling radius using 72 events. And hotspot is found here. And global significance was estimated to be 3.4 sigma at that time. And this is an updated result using TASD 12 years data. And the latest result is still, the global significance is now estimated to be 3.2 sigma. And little bit lower energy. Also, another excess was found recently, above 10 to the 19.4 electron volt. And this is also drawn significance map as previous slide. But this is also equatorial coordinate, but the center of this figure is a little bit is shifted like this to locate the new excess at the center of these figures. So this figure, hotspot, is shifted here, and the new excess is drawn like this. And this is a figure above 10 to the 19.6 electron volt, 19.5 electron volt, 19.4 electron volt. And each significance was estimated to be 3.6 sigma, 3.6 sigma, 3.4 sigma, and using 20 degrees oversampling radius using 11 years TASD data. And also lower energy. Already Auger discovered a dipole anisotropy for above 8 eV at more than 5 sigma significance. So we also doing the similar thing for check. And this is a map above using the sky map of residual intensity between TA data and an isotropic distribution above 8.8 EeV because of 10% energy shifted because of to rescale energy to do the same analysis with the same energy threshold with as Auger. And this is our result so far. And the result is not significant yet. But data is, the result is compatible with Auger results so far. And about interpretation of anisotropy at the highest energies, the correlation by directions with astrophysical sources searched by the Auger and TA anisotropy working group. And this is to combine the two data set, Auger data above the 38 EeV and about TA data, about 49 EeV data is used in this analysis. And the correlations with sample of nearby starburst galaxies and 2 mass 2 MRS catalog galaxies were searched. And angular scales and energy thresholds were also scanned. And this is actual the rescale function of energy between and Auger. And now this is the best the expected flux map with a model of starburst galaxy. And post-trial significance of the correlation is with starburst galaxy is rather high and now estimated to be 4.2 sigma. Okay, this is obtained. These are obtained implications of anisotropy results so far. And also I show some composition results. And this is a measurement of X-max using TASD and FD hybrid events. The black point is the data point, and the hatched region corresponding to estimated systematic uncertainty of the data. And red and purple, orange, blue points expectation from Monte Carlo simulation, assuming proton, helium, nitrogen, and iron. And right is, the left is a result of a mean X-max, and the right is sigma X-max result. And this is studied still in the limited energy range between 10 to the 18.2 electron volt and 10 to the 19.1 electron volt. So if we want to extend to the higher energy, we think more statistics are needed to study. But so far, we compare with QGS-204 interaction model, expectation is compared with the data. So, and as we can see from this result, the data looks like data is agree with light composition. And also using the new technique with TASD, each event the resolution is worse than the X-max, but statistics is better than FD. So this technique is also conducted. And this is machine learning technique based on the boost decision tree, and 16 composition sensitive observable were used for this analysis, and using 12 years of TASD data. And this is the black points and purple, orange points the result using the TASD data. It needs still more statistics, but also result looks like consistent with light composition using a QGS-204 and 203 data, interaction model. And using a TEO FD, we also extend the composition result to the even lower energy, like this. And we extend the composition result go down to 10 to the 15.8 electron volt. This is the result, and as the previous figure, this the data black data points are compared with expectation of Monte Carlo simulation, assuming some composition: proton, helium, CNO, and iron. And this is the data points without comparing Monte Carlo, and so this is hybrid results as in the previous figure. This is looks like rather continuous, connected to the higher energy. And from this analysis, the breakpoint is estimated to be 10 to the 17.291 electron volt. And also the using the similar analysis with composition using TASD, the ultra high energy photons are also searched, but actually UAT photons were not detected so far. So we keep updating the upper limit of UHE photons. And this is updated upper limit here. It's a result using TASD 11 years. And this is expectation using some astrophysical model. And it's rather, we are updating the upper limit like this. And the left is upper limit of integral flux. And the right is upper limit of directional, the flux upper limit. This is, okay, what we obtained using a telescope array experiment. And as I emphasized, we got some implications of anisotropy, or the highest energies. So to examine the implications of anisotropy at the highest energies obtained by, thank you, TA, we started develop a TA times 4 experiment to accelerate the pace of the data collection at the highest energies. And our plan is 500 new SDs. Here, this region and that region with 2.08 kilometer spacing. And the new SDs and the current SD totally cover 4 times larger detection area. This corresponds to about 2,800 square kilometers. And already more than half of the new SDs were deployed in 2019, and the deployed SDs are running stably from 2019. And also, we already constructed 2 new FD stations. And one is already stable running from 2018 and 2020. Other south is a stable run from 2020. Then, okay, so I just briefly look at the result. We already measure the energy spectrum. This is a footprint of TA times 4 new analysis with just a new detector. And this is the black points preliminary energy spectrum with newly developed, only with the newly developed detector. This is consistent with previous energy spectrum. And this is monocular FD, new FD results. We continue to observe with these new FDs. There was a little bit shut down due to coronavirus, but we continue to observe, and we obtained consistent energy spectrum so far. And then also we made a hybrid trigger to obtain rather lower energies. Yeah, actually, TA times 4 SD is rather sparse, and energy threshold is a little bit higher, and 30% efficiency at around 10 eV. But we implement the hybrid trigger, and we improve efficiency. And this is actually obtain the energy spectrum with the hybrid events. And finally, we expect 3 times larger SDFT equivalent number of events if we complete the full TA times 4 SD. And this is a future prospect of TA times 4 experiment. We already finished half of TA times 4 SD, but still half of them are remaining. So we are planning to construct the rest of SDs in next year. And we are now also investigating the analysis for anisotropy and a composition with new TA times 4 detectors. Then also this is for even lower energies, there is also update is planned, and even denser, even more dense SD array is planned at close to the tail FD, and this 54 ASDs will be deployed this winter. Okay, this is a summary. This is the TA experiment continued to observe from 2008, and largest detection area in the northern hemisphere. And the rival direction, we found 3.2 sigma hot spot above 57 eV, 3.5 sigma excess of 10 to the 19.4 electron volt, and the correlation with starburst galaxy, it's 4.2 sigma significance, and the spectrum declination dependence also claim that 4.3 sigma, and these implications of anisotropy being updated, and also we constructed a new detector, so we hope confirm these implications to find out origins of ultra-high energy cosmic rays. And we also still anisotropy and composition analysis is ongoing. We will present it in the near future. Thank you very much.
All right, I think we have time for a couple of questions. Point, but don't put there.
Oh, I'm sorry. Hi. Okay, let me go back. Yeah, this is actually here. This is bending of a galactic magnetic field is not considered at all. Yeah, it depends on the which composition of cosmic rays contribute to the anisotropy. But in case of protons, the effect will be small. In case of silicon, yes, lens. Yes, you mean the lensing effect. That's you mean the yes. If you assume heavy composition, the field of view is limited like lensing. Yes, I understand it. Even if yes, that analysis is ongoing, and that effect is considered, then yeah, that's yeah. That, even if that is considered, the lighter composition, the effect is still small, and the middle is rather yes. If a heavier composition, that's the source direction will be changed, so the source will be different. Yeah, in that case, yeah, that's if real, so the real composition measurement will clear out this estimation. This expectation is reasonable or not in the future. Yeah.
Right, so I think it's time to move on to our next talk, but let's thank our speaker again.
Our next speaker is going to be remote.
Oh, I see. Okay. So this Petra is going to give us a talk on using ground-based.
results that have been presented by a school of experiment that are shown here on the screen in the last decade or two. So it's okay. So just to remind you a little bit of the complementarity between imaging atmospheric shrink telescopes and particle detection or detector arrays. The idea is that as opposed to IACTs, particle detection arrays really only take a snapshot of the shower as the air shower as it strikes the Earth, and therefore recently they have an even very about 4,000 meters in order to get a maximum amount of information. Particle detector arrays typically consist of Schreck detectors, scintillators, or PCs, and sometimes a combination thereof. The major advantage of them is that they have a high duty cycle. So typically they have an uptime of about 95%. They have a wide field of view, and they have good sensitivity, angular resolution, and energy resolution, especially above the So that makes them particularly suited for visual transmitters, extended and large scale vision, and highest energy accelerators. So regarding the wide field of view and high duty cycle, so typically PDAs have an instantaneous field of view of about 2 steradians, which is about 50% of the sky. They can have a larger field of view. It more depends a little bit on where you make a cut in your analysis in terms of zero area. So typically, most of the results previously reported used the zero area from 5 degrees, but some will go below that to 60 degrees, for example. A full survey then gives you 8.4 steradians per day, and you see down here an example for a field of view with a Auger detector as it sweeps across the sky to the left, and then produces what you see here in galactic coordinates sensitivity map that shows you where the PDA is. So in the case of Auger, most sensitive was its location in Mexico, and then not so or not at all sensitive in the southern hemisphere or the farther north hemisphere. And again, as a reminder, this is 445 degrees Celsius. The sensitivity versus energy, again, in the case here of Auger, because I'm showing my regions here as a Auger member. This year shows the measured significance using the Plenary of 2017, using 507 days of data. That is the sensitivity of the WC catalog from 2017. And then there is a projection to 5 years of Auger data. This may be even better now since then Auger has updated their reconstruction algorithms and gained in sensitivity more than its projected one. In any case, what you see here, what I want to point you to is the intersection between this PDA and Hasbro and Magic, for example, as examples of ICTs for 50 hours. And that is just below 50. It's just below 10 dB. So really complementary to IACTs in some ways, especially when it comes to like searching for things surveys discovered. So the recent results from PDA can be grouped, I think, in 3 different groups: the survey capabilities and high duty cycles. So results that come from this feature, extended and large scale emission sensitivity, and then high energy bandwidth sensitivity leading to measurements in unique phase spaces, for example. So again, not enough time, too much to talk about, but I just wanted to list essentially some of the results. So, for example, Bob has presented at conferences long-term monitoring of material 421 that then also allows you to catch those flares that may happen without notice. And then below that, you see a measurement of such a flare from such flares from material 501 that monitored the source from 2008 to 2012, and then was able to measure the energy spectrum of these flares. And then, of course, there's this paper that shows you the power of multi-messenger measurements, where IceCube discovered high energy, really very high energy neutrino from TXS 506. And then that led to a campaign of follow-up measurements, of fiber measurements, in order to pin down the physics processes of these sources. Now, there are other examples. For example, for the extended source emission, Auger discovered what now has been established as its own source class, a halo, or two halos rather, surrounding the pulsars, the Linear pulsar and the monogenic pulsar. This has then led to a slew of papers and follow-up observations. For example, low energy can has seen halos or detected halos. The interpretation, the fundamental interpretation of these halos is still out. But what we know is that it is, and you see some of these molecules to the right, what we know is, think we know is that it's a distinct feature that is not the classical pulse and pulse in the nebula and not the supernova. So it could be that it escaped, for example, or that it's just what is left over after the supernova dissipated. But again, that's a lot of work being currently done trying to understand these gamma-ray structures. And then finally, very large-scale structures. What is sort of the very bubbles have been constrained at these very high energies by Hawk, excluding at the time a hadronic model. And then also Hawk has probed gamma ray emission from distant molecular clouds, thus allowing us to understand it's a cosmic ray spectrum, and flux is the same or similar to what we are measuring biologically. And this is starting to put, as you can see here, some really constraining measurements on this. And I invite you to look at some of these applications. So, now a few more words on surveys. So surveys over the years, this summary should show you kind of how much progress has been made in gamma ray astronomy with PDA. So Milagro published in 2007 a survey of the galactic plane, combining 7 years of Hawk data, 8 sources and about 20 TeVPA were reported. The parameter in this data set was 15, that's measured at 15 cm. Then Auger followed shortly after that, detected 10 sources above 0.3 TeVPA, and in their sample, the parameter was detected at 20 cm. The most recent published survey is the 3HWC catalog. It's based on a little over 4 years of Hawk data. In this survey, 65 sources were detected at a significance of greater than 5 sigma. 20 of these sources were away from previously detected TeVPA sources. 14 of these are potential counterparts of the corresponding catalog. And the parameter in this data set was detected as a N190 sigma. Another word on the complementarity with IACTs. There's an interesting study published in 2021. Hawk has some collaborators who are also members of the HES collaboration, so this is how this came about. And what they did is they kind of adjusted the HES measurement to simulate what a Hawk data set would look like by kind of increasing the PSF of the HES data set. And then approaching the Hawk PSF and also adjusting the background estimation. And what they found is that out of 7 of previously undetected sources, now 4 was able to detect in the same equation. This is the manipulated, if you like, prepared, specially prepared has data set and Hawk data set. And the other 3, they determined were not, the Hess analysis was not sensitive enough to measure. So in other words, what this means is, number 1, the Hawk and Hess measurements are consistent, and data sets are consistent. Number 2, there is something to be gained to what everyone field of instrument measurement that is potentially more suited to measure extended sources. I think also it's already looking pretty good, but I think it gets better. So Hawk has very recently started showing results from their past 5 data, which has improved harmonic injection and angular resolution, and also now looks beyond 45 degrees zenith angle. And so you see kind of the difference between the 3HWC catalog map and the new map, and you clearly see there's a lot more structure to be understood and analyzed there. This is also, of course, past 5 more days of data. So, in addition, and that was, I guess, the big news last year, is that we now have between 10 and 20 Petra candidates and counting. What you see here is a map from the Nature publication by LASO in 2021, and they detected 14 sources at very high significance that corresponds to 530 ultraviolet photons, and that is really impressive. Only 6 months of KMT data, so half a year of data from one of their subcomponents. Hawk, on the other hand, started showing results this year, where they reported now 80 sources and more than 2,000 days of data above 100 TeVPA. That's up from 3 sources that were reported in 2020. All right, so interesting stuff. In neat agreement with that, Tibet also at about the same time came out with a result with a national sub-PV diffuse emission that is gamma rays above approximately 400 TeV, observed away, so 0.5 degrees, I think, away from known TeV sources, and they appear to be kind of centered on the galactic plane. That is strong evidence that cosmic rays are accelerated beyond PV energies in our galaxy and spread over the galactic disk. I think we will hear more about this afternoon. Then, of course, there's a high-profile publication again from LASO that identified the Petra nebula as a tevatron. The LASO measurement that was published in Science last year covers 3.5 decades of energy. It agrees with experiments below 100 TeV, or it has a recent agreement. Also, it shows the results from the WCA, the KM2A, that shows that they are consistent in the overlapping energy region. And then what they did is they looked at, they performed a fit, assuming electronic model, saying that the highest energy electrons that produce this gamma ray emission are greater than 2 PeV, and that they are accelerating in a rather compact region, and that this would mean that the acceleration efficiency of this, of course, unique source is about 1,000 times better than SLR short waves. One thing I wanted to point you to is here in this model to show here, you see that there is a discrepancy at the highest energies, about 50, 60 TeV, or to 500 TeV, and then you also see this excess they are speculating in this science paper that this might be due to the fact that 1 second. And Park has measured gamma ray emission from this region in 2021, which was reported to be between 10 and 1,000 produced by up to 1 cosmic rays. And these cosmic rays show an emission that is slightly more common in nature. And to the right here, you see electromagnetic spectral energy distribution and the extent. And so, what's interesting here to note is shown in the next slide. If you actually look at this region, this complex region, right? And so you see emission from several source components. On the left is the measurement for long, right? It's the measurement after the Sarazin contribution, and the gamma signal contribution is subtracted. And this is what's shown when it's the Sarazin and distribution. So what this shows, again, it's semi-transparent overlay, is that the bias source data is extremely important. Another example is of the power to improve the angular resolution is the Plenary region. So there had been a measurement done and published by Auger of this region, and it was, since it was co-located with the very close measurement, it was a combined fit was performed. And this combined fit predicted or concluded from this combined fit, it was concluded that this initial quantity is produced by 800 up to 800 photon in 1 Since then, there was a measurement by TeVPA, so going into the same direction. Also measuring emission excess of 100 TeVPA, and then of course last report in the Nature paper, the measurement of about 570 photons from this region. Problem though is that it's also a complex region. Where does the emission come from? From the Sarazin nebula in the region, or the spillover remnant, or the combination of the molecular cloud. So morphology studies will be helpful. What was found recently, just in time, was that Hawking now resolves two sources of this region. And this is in accordance with magic that you see two sources as well, which they interpret at the head region and the tail region of the instrument. And so the head region is in the upper source, and the tail region is in the lower source. So the studies of this are still ongoing, but we can probably already say that they will extend the magic spectral energy distribution measurements to higher energies. All right, and then finally, last but not least, wider field of measurement of X-ray vibrates and vibrate systems and microquasars. I just wanted to show this science report or science publication article from 1993. At the time, Cygnus and X3 and Hercules and X1 were one of the sources that people suspected could be responsible for the cosmic ray acceleration. Since then, unfortunately, and then for a long time, binary systems were rather a disappointment in terms of cosmic ray acceleration highest energies. That also, I would say, in the recent few years has changed. So this is one of the results that we reported. It's the emission of greater than 20 TeV cameras for LS-39. And there's also now the separation of the emission between high and low state, but I would prefer you to talk that we see the happening on Thursday. Again, though, multi-source splitting is the issue, the key here. Then 2018, when we result, what's the nature of emission above 20 TeV by SS433, rather than jets of SS433, and you see here that the jet structures overlaid, the loads overlaid with Hawk detection. And this now has been confirmed by HES. So interesting results here as well. And then the final result regarding binary systems, the microquasar, there has been now detected gamma ray emission from the direction of the actual binary B4641 Sagittarius. And again, 20 TeV, above 20 TeV. So these sources have the potential to really accelerate particles to high exponents. And finally, there is now detection of the galactic center with Hawk. But again, further details are to come. The preliminary spectrum appears to be comparable to the HES measurement. And then, of course, these PDAs can also test fundamental physics like Lorentz invariant violation and unique phase spaces, and that's shown here. That has to do with the highest energy and long distances that we are dealing with. So, what's next? I think that we can go to the next here. So, next is among other projects, the Southern Wide Field Observatory, hopefully. There has been a paper submitted, a white paper submitted to the ASCO 2020 process, and I like this little overlay here, the little it shows you when you look at photos and all the things that you can do with them, there is a lot of stuff to be done, so photos are important. Anyway, the paper on particle astrophysics and gravitational evidence contributions by the S to SWGO and advancement to and then you see here kind of the timelines for the different projects, but I'm sure most of us is already. So SWGO is a project that is a collaboration that consists of 54 research institutions, soon to be more. And you see kind of the map of the institutional members and supporting members of this project. Really built in South America, if we get the money. And currently for both country candidates are under investigation, are being explored. Bolivia, then Chile, Argentina, and Peru. And there are a different number of sites in each of these. In Bolivia, for example, one site in Chile, and then 2 sites each in Argentina, and 3 sites in Peru. I should also mention there are other efforts that have a somewhat separate focus. Okay. Condor and Chile and Petra in Bolivia. So really interesting to see. The sensitivity curve here shows that again overlap with CTA is in the same range as with the current projects in operation. Anyway, I think final comments, particles in ground-based particle detection arrays led to unexpected, sometimes paradigm-shifting discoveries, multi-instrument and messenger analysis will provide unprecedented science output of an astronomy with current future. Experiments making crucial contributions, and then And principle of open, I wanted to make that point, and I've done it most of my talks. It's really important to follow the principle of open science and publicly available data in order to get maximum science output. So, yeah, I would like to mention initiative for very high energy open data format. And finally, cosmic rays and thank you.
So I think we'll take time for one brief question. Okay, well, this will help us get back to schedule. Let's thank our speaker again. Next, we're going to hear about Jay.
That's also really weird. Yeah.
Also remote, okay.
Thank you very much, Petra. Frederick, share it, right? Yes, we can do that.
Alright, perfect. Yeah, so I'll start. So thanks to the organizer for providing the unfortunately here in person. Unfortunately, on COVID this week, coming back from Europe, so I have to cancel my trip to Vincent. So let me talk about the latest version of the Geology Observatory in Sarazin. So you probably heard about the Geology Observatory already. Its goal is main goal is to measure the energy to cosmic rays based on how energy is about to both. It's located in the Mesa province in Argentina. It's a very, very large detector. It's already about 3,000 square kilometers. That's about the size of the state of Ireland. Baseline design as a surface detector is made of Russian oxide about 1,600 levels. Range of about 500 1.5 kilometers apart. And then there is a fluorescence detector that is made of a 27 telescope that is already the array to measure the fluorescence detection. Alright, now if you actually look on the side here, you have actually a sub-array detector which allows to make some measurements of low energy with PhD. It also has a little antenna which is very array, so you have some of the things that we can take in the ground as well as on the ground examples. Okay, so from the presentation from Kido side, it's the array, we know about fluorescence detection, surface detection, so I'm not going to spend very much time here. Fluorescence detector is measuring the HTTP profile of the shower during nights and nowadays nights. It has a basic energy method, so it sets the energy scale for the emissions cosmic rays. The HTTP profile allows you to extract the quantity of X mass, which is composition sensitive. Now, the problem with the fluorescence detector, I would say, is that it does only a 50% cycle of numbers from the fact that you can make those measurements. The statistical engine of the observatory is the fluorescence detector. It has a factor of around 100% that is measuring the shower density, the cosmic density, for the export distribution. As you heard from Kido said, here we actually use a proxy to measure the energy, but it's eventually calibrated to the end. Now, the new power is the radio detection technique here, which is known for a while, but this is a bit more for ultra-energy cosmic rays. And this also allows you to measure, to make a parametric measurements of the energy scale. And it's also mass composition sensitive. All right, so you've already heard as well that Auger is undergoing an upgrade to a previous version 1. For the purpose of this talk, we are talking about phase 1 and phase 2. Phase 1 probably ended sometime in 2021, with a total exposure of 80,000 square kilometers per year for the vertical shower. It's a shower with some temperatures more than 60 degrees. And so phase 2 is about to start. As we continue to deploy some of the station we are mentioning this in a second, projected exposure is going to be about 40,000 square kilometers situated steering here for the vertical shower. Okay, so what does the upgrade consist of? It's basically for every one of these watershed detector, which I mentioned as WC later on, where basically detector, what's so-called SSD, and then a radio antenna. So effectively, this method of the observatory because the cross-section of the SSD was small, was shallow, always in those shallows, and so there the radio is going to be taken. Okay, so we got some data on from this quantum engineering array here, which is still the way we deployment, and there's been scaled out in the process of engineering. All right, so let me try to put in a nutshell what we are trying to do with this subject. Well, first of all, as we're going to do here, mass composition is critical for everything that we're going to be doing with the observatory. So what we want to do is we want to achieve to collect this mass composition information on a regular basis using the 170 factor of and so what we do here is we have this integrated detector, so the electrical shower, where we're going to be able to measure effectively independently the electromagnetic part of the shower and the part of the shower. So from the electromagnetic part of the shower, we can get energy. The reason why this is important is because if you want to use mass composition from the SD, or if you need to relate neurons, the number of neurons which you have to mass composition, you can only do that if you measure the energy independently. So effectively, the SSD is to measure the energy of the shower, and then use the roots to measure the neurons. But now you can bring down the energy. So you bring down the energy and number of neurons is directly related to the composition. So that's what we're going to try. And for radio, I would say this is the same thing. Except that you can take the radio signal to measure the energy, and then use the WC for okay, so you've seen the spectrum for TeVPA already, the spectrum for Auger as a lot statistics because Auger is much bigger than TeVPA. The latest results is basically an extension taking into account the analysis of shape of rich units, which allows an extension that down to 10 to the 16. But overall, if you look at all the different methods that are being used to build the spectrum, they can be added together with a fairly small amount of normalization with the method, definitely below the total energy scale. So once you combine all those methods, you get this really beautiful spectrum that shows all those different features that we have known in the past that have been shown also telescope array, separately the anchor, and the flux suppression. And you see this kind of feature where this kind of flattening, we have to go through the flattening of the spectrum will be step here and get kind of relate this to the fate of the probability. So I'm not going to talk very much about the shape of the spectrum yet, but it's not, we don't learn very much about doing a fit and find out where the transitions are occurring. But what matters here is how this is going to be fitted on the subject of astrophysical models. So I'll get back to this. This is a combination of all the spectrum that are measured by the various customer experiments, low energy, high energy, OTA, and Auger. Here we've already had a discussion about how we can basically see how we can show that Auger and TeVPA kind of sync to every scanning the energy scale up to about a certain energy, let's say about 3 10 to 19. Then even when you look at the quantum information band, there's some energy dynamic shape that prevents the experiment. I just want to flash quickly this slide here because Auger experiment we put on a big cycle using the telescope array to operate to the battery, able to do construction, telescopes, and so on. We hope, or at least understanding the difference in flux, and actually understanding the aspect reconstruction biases between the two experiments with deployment is not next month. It's pretty exciting. The example is basically going to be both the operation of maybe SSD detectors. So we're going to have to watch separate, we're going to be able to separate detect across many versions. Okay, moving on to composition, basic features hasn't changed for a long time because we are in the process of working with group and this is for composition. So as you probably seen before, get the line composition that somewhat lower into the input and there was a transition to this composition that gets later as a function of this is both seen in the range of experts and the rate distribution. One thing that has been done recently, is to analyze SD data and through a recalibration process of the lenses done from the channels compared to the range of ground. We're able to actually get a very, very nice rate between FT and basic data, and we're able to extend the analysis to another country. Now, this recalibration is something that we'll discuss in a few slides. Now, with respect to phase 2, I hope here you understand why we want to put so much emphasis on trying to merge the composition with surface detector together as statistics as possible to be able to extend this analysis here and eventually select as lines versus as composition basis. Okay, a new results from Auger has been the analysis of data of Auger so it's a pretty small array, contained as a very close to one pattern. But we know from radio detection technique that this sensitivity expects. So this work as well, with these statistics this data here at the beginning, and from the biology, what you're able to show is that there's a good method. And what's really interesting about this is that both the resolution, is actually comparable to the systematic is actually different. So with respect to energy scale and with respect to composition, actually we're able to reduce the systematic errors of this method. And then, of course, for radio, the advantage of ID is that it's consistently 100%. I know from the radio, we don't have to rely on the version of machine. Okay, so I did mention the scaling of the data collected with the SD that provide effectively that's because there is not a lot of negative access to about 40%, and it's also the data that the interaction. The issue with the US composition is that the two rely on interaction to define what the US composition is. And so this is actually demonstrated both for the hybrid, basically detecting fairly low energy data, that the data that are collected really goes to this relation from and so this is known pretty much as the puzzle. And if you want to know more about the origin of the puzzle, I would direct you to the talk of this on Friday. There was some discussion with this demonstration, so I will paper. I tell you already that this is really so it's going to tell you a little bit about that. But we found out in the field, actually study the fluctuation of the ideas is that this actually seems to be very similar to what's predicted by the model. So that seems to indicate that it's more like fluctuations during the first interaction. During the first interaction, the effective so not necessarily very good particle physics, but more like something that is okay, so I think you understand why this kind of SSD combination for one shot will allow us to collect this information, more information more statistically than this. But again, if you want to make that eventually, you need to make the composition measurement properly, right? You need to fix the values. So the expectation is that in the next 5 to 10 years, we're going to be able to solve the puzzle. We are going to be able to create measurements, real measurements of the individual interaction in this composition. And that's that's really critical for our people. Okay, so now once we have the spectrum, we have the position, we get the fit. This is going to be really the truth to the spectrum, because now you can see the fit actually is. And so I'm not going to go into detail on do this, but you can see how you can fit the position. You have to move towards higher passes, bigger passes, as you go higher. And so when you do that, you are basically forced into a scenario where protons are going to die fields, then it's going to be taken over by a big scale, and something bigger and single potentially fit into iron, which is not actually rich. And you can see how the evolution of the fraction of the field here. And it's very, very hard to do something different. And so this really points out that actually basically the GTP scenario, the GTP cut off the order of 1.5 to 18 volts. Right? So if you think about photon, it means that the cutoff is not something about 1.5 to 18 volts. That is really, really far from what you would expect of the first pressure will be Okay, so that also seems to indicate that the chance of having a significant fraction in the highest dimension has to be fairly thin. And so this of course, it has huge consequences and beautiful. What I'm going to mention next. So you're probably aware of the results of the recent results of Auger, which is the discovery of the dipole is not centered around the energy center. Now, the energy of this dipole is not 6%, but it's highly significant at 6.6 sigma. The dipole opportunity actually increases in energy. This is observed, and that's the level of significance here. It's going very close to this 6 sigma because statistics are close to actually important. The location of the dipole appears to change very much until we reach higher energy here. This is basically critical to tie in with filtering the greatest energy which is inside. So going to decision to get the highest energy, the first thing that you can do is one source of the sky. What you find is a warm sky that's around say once you stick up this trial or the angle, an energy level of 4 degrees. Now, all those 24 degrees are actually going to get a few sources here. All of them Eiji identifies some of them stars. So, there's a question about what the sources could be. So, if the feature is big, well, first, the physical question of saying that it's 10. In this case, you get the double same output as the question is but maybe more interestingly, of course, we can start with chemical researches and we can see here around the 2 and we are watching for the ground how the energy has the smallest galaxies and see how this constant and this constant here appears to be correlated with the stars and the notice here that there is a little bit of flux in this hemisphere here. There is a star that has here. So that would be very good. Notice also that there are some stars in the colored sky, which is in the similar scale. And so this is where the star highest frequencies of them which is made with stars. Now this is the proof of the signal over time. You see that the signal is going pretty much all of those different hypotheses here. It's really dispersion from the starless galaxies here. At some point, there is a chance that declare the ICR sequence, the ICR sequence here, with the signal on the way of the drop here. Still feels significant and still well within the expectation of the growth trend. So the idea, what we're thinking about is a discovery of the level of gases which is sources by the Jewish problem. It's So if you add to this the ability to do customization analysis, where you probably actually want to learn more about those sources if you're able to identify let me go through quickly for this one here. That's what we call composition and solution studies. And this is something that is very possible because all the statistics are here. So even if you consider the activity, you can basically take the data and say, make some using a simple assumption and say, what is the difference between the composition that we consider scenario, assuming that Huentemeyer has a stronger negative field and therefore more deflections in the way. So you can do this, and I'm not going to go too much into detail. You get the pattern of this, which indicates that indeed it looks like you have a linear composition and lighter composition of now, the interpretation here is quite complex because it depends on the closest distribution, it depends on the horizon, the horizon, and the correlation difference. And so, simple is what here in my dimension, which is signal as well. But this is really to highlight the power of the algorithm and mass information because of collecting the mass information. Imagine that instead of data from the AD, data from the ST, you got about 6 times more data today than you actually have to make those things. Okay, I have extended a bit of time, so that's good. I want to mention very briefly a very promising approach based on that is going to become more important in the field, and that's machine learning in general. So here's an example here of what you can do. So you can take a simulated hybrid data set. So what you have here is you have the X-max of the data, but you also have the ST traces. The ST traces for all energies and for all different libraries here, you will have a bunch of things on the machine learning of this here, and actually we can basically extract quantities that are related to how we can trace this, what we can trace this to the composition. And out of that, what you use is try to extract the X-max. And you see this is really remarkable. Compare the X-max with the power to the X-max and the network. What you get is a very nice bias correlation between the power and the however, when you apply this to the data, you actually see this correlation with the bias. This bias is about 31%, which is correct. Right? So that's to indicate that the method works, but it's suffering potentially from again some issue between what we see in the data and the model. That could be related to the puzzle again. In fact, those models in this maximum are going to be shallower than the real extent which come down to the composition, which can be explained by the fact that there are low minerals in the data there is in the methodology. Now, in phase 2, of course, if you have a handle or better handle on the real, you think you can solve it positive, then you're going to be able to get something like correlations actually. So that's powerful in itself. It's even more powerful because now you can take the data from phase 1, apply the machine learning technique, you can basically analyze the data. So that would be extremely powerful. All right, I'm going to do really quickly unfortunately to those. We're able to meet the ability to minutes here, which is an excellent neutral energy, I should say neutral energy, but neutral energy photon neutrino detector. And of course, we have to keep in mind that if you ever discover usefully a photon, especially a neutrino, whether it's an intimacy or not, that's really a game changer for you. All right, so let me conclude here and celebrate what I've said earlier. Let me put this in slightly more context. So I was a leader want to put this a little bit in context, project plan in context of this work here, which is 10 or 20 years in the future, considering experiments and experiments. Okay, so what we have here is a diagram that we made in order to try to explain what the goals of the triangle possibilities are. There are twofold. The astrophysics side, the cosmic frontier. And then here you have source identification, which are particular astronomy, is kind of awesome. And then on the particle physics side, on the energy frontier there, what we're trying to do is figure out whether there is good quantum physics and the highest energy, including potentially the highest energy physics. And those things are, there are a lot of fields in our basic physics. But first, where we try to cosmic rays can contribute. So, as I mentioned before, if you have a way to bring out the energy with the real components of the detection, if you have strong real electromagnetic simulation, you are very likely to go the interaction there. And that, with the help of the accelerator, means to actually solve the puzzle. Now, if you solve the real puzzle, you can get a better performance. And the mass and the energy together allows you to do, even if you have mass with the resolution, if you have both energy and some unity composition and some social, you are going to be better in terms of the social, you're going to be better in potentially identifying resources. Now, let me show you where Eiji is going to contribute. It's going to contribute here in another direction, it's going to contribute right? And it's going to contribute here, I'll show you the stuff and we're going to the composition. Now, here's the thing. If you have good enough resolution, you have good things in the best resolution, then you can start doing visually or studying, which is much better for the internet. You see that this is the only system experiment that they should do that. What you can do then is you can self-regulate about this is going to be way more powerful into identifying resources and eventually the resources. And it all comes down to this, right? What is your next resolution? What is your resolution? In the white paper, we kind of define this box here. That basically shows the range of plans that to do. What we have just in the last 8 months, we've been working on the paper as a machine. It seems to be taking the real resolution and making it better and better to the point in which at some point we think it might be the one of these boxes here, which is going to be starting to be competitive with even what you can think as a next generation experiment. And so that's really exciting. And so I really want to emphasize that project one is to prepare the projects and it's critical to achieve this vision where it's going to go 10 to 20 years in the future.
Right, we'll take time for 1 or 2 questions.
So if the shows up in the expert distribution, what will be the area of energy distribution is Sarazin. But compared to this right now, the show will not experiment
Did you pick that up, Fred?
No,
You might want to just come forward, because I was actually having trouble understanding everything you said through the speaker. So, do you want to just come up and ask your question? Yeah, just come up. Thanks.
Yeah, okay, so concerning the ion laser, this is showing up in the X-max distribution, but I'm wondering what would be the effect on the energy distribution, especially if we're also measuring some differences in energy between Auger, for example, Tesla, right? Would it go in the correct direction or the opposite one?
let's see. industrial question. So when you consider you want to measure the number of units goes by the composition. So if I understood the question correctly, goes into our the resolution. So the energy scale for things about 50%. It's actually quite good. The better, of course, the better the energy, the less this contributes to the uncertainty analysis. And so if you look at those plots where you see that the rates and those rates, well, in some other plots, you see that the rates of energy uncertainty. I would say that this is not going to be good. Does that answer your question?
Maybe I send you an email because thanks anyway.
Okay, on that note, we'll arrange for lunch. Thanks for the speaker again.